Hi Chemistry. This week we're getting heavy into acids and bases, so buckle up. Today I'm going to tell you about Bronsted and Lowry. They're two chemists and they were classifying acids and bases. Okay, I'm going to introduce baking soda. You're familiar with it. It's typically considered a base, and it's because it raises the pH of neutral water. So if you mix baking soda with water, you get a basic solution. All right, but check this out. If you then take that basic solution of hydrogen carbonate, which is the active ingredient in baking soda, and add it to sodium hydroxide, you find in drain cleaner, the pH will actually go down. So hydrogen carbonate can act as an acid when it's added to hydroxide. Okay, so it acts as a base with water, but an acid with hydroxide. What on earth is going on? Let's break it down. In water, here's what's going on. So that HCO3, hydrogen carbonate, baking soda, reacts with water, gives you that H2CO3 and hydroxide. Okay, by producing more hydroxide, you're making a more basic solution. pH goes up. Now, if you add it to sodium hydroxide, the sodium ions are spectators, don't worry about them. Okay, so our baking soda with hydroxide will produce CO3 and water. So check it out, hydroxide's leaving the solution. That is going to lower the pH. All right, so is baking soda an acid or a base? Well, we got to be a little smarter than that. Bronsted and Lowry don't talk about things as acids or bases anymore. They talk about whether they act as acids or bases in specific reactions. Okay, so the new approach to classifying acids and bases focus on the reaction rather than just the solution. Okay, so you no longer say this is an acid, this is a base. You got to go more in depth than that. So, moving on. Let's dig into this. Baking soda and water. I want you to focus on the hydrogens. This HCO3 become H2CO3. The only difference is a hydrogen. Where'd that hydrogen come from? Well, water lost one. So this arrow is showing you a proton transfer from water to hydrogen carbonate. This sounds a lot like redox with electrons. Okay, acid-base reactions are proton transfers. It's crazy. Okay, so HCO3 in this reaction accepts a proton from water. Okay, and just to make it clear, maybe you're confused by the words I'm using, a hydrogen atom is a proton with an electron buzzing around it. We don't really care about electrons in this unit. So H is a proton. Cool. Let's talk about what happens in hydroxide. HCO3 becomes CO3, it loses a hydrogen. The OH picked it up, became H2O. So this H, this proton, left HCO3. So HCO3 can accept or donate. That's why it was acting as a base in this reaction and why it acts as an acid in this reaction. It's all about what's going on with the proton. Okay, here's the money part. Bronsted-Lowry acid donates a proton. A Bronsted-Lowry base accepts a proton. That's it. Got a quick example. A brand new acid-base equilibrium system. We're going to identify the acid and the base. Okay, just on the left. We're not going to worry about the right. It goes both ways, but let's only worry about the left. You're most interested in the H's. H2CO3 became HCO3. How does it do that? It's got to give up a proton. The only place it can go is to this HS, which it did. HS became H2S. Okay, so a proton was donated like that. If you donate a proton, oh, does that make you an acid or a base? We wrote that down. An acid is a proton donor. Okay, that's our acid, H2CO3. The proton acceptor is our base. Cool, right? Tying it back to baking soda, You want to know this? Something that can accept or donate protons, like baking soda, HCO3, call that amphiprotic, which is a cool science word. All polyatomic ions involving hydrogen are amphiprotic. So we actually saw another one here. This HS would be amphiprotic. It can gain to become H2S or could lose to become a sulfide ion. Cool.